I think we can start. Welcome to the first Analysis and Mathematical Physics seminar, and welcome Professor Pavel Kurasov from Stockholm University. Today we talk about higher dimensional Fourier quasicrystals from Lagrange varieties.
Okay, thank you very much. So first of all, I would like to thank Peter for inviting me here to give a talk at this seminar. Yes, and this talk I will present our recent results which we obtained together with Laλδλ and Cynthia Vincent, that you should probably know, at least some of you, because they have been here, and Mario Kummer, he is from Germany. So, but first of all, I'll start with some kind of slow introduction. So, when mathematicians speak about crystals, yes, what kind of abstraction they think about? So, one can think about points in some d-dimensional space as places where the atoms are placed, yes? And then the first important concept that was formulated was the concept of dland sets. Dland sets, these are discrete sets in idea such that they are uniformly distributed, which means that there is a minimal distance between 2 points from the set. And the second thing, that they are relatively dense. So it means that there are no holes in this set of arbitrary large operators. Yes, and of course the first example of such set is an ideal crystal. The ideal crystal can be thought about the following: that you have a full rank lattice L and some finite set, and you look at all translations of this set by this set. And of course, with such sets, you associate a Poisson summation formula. Yes, Poisson summation formula means that if you take values of the function at this lattice, sum up, this is the same as to sum up the values of the Fourier transform. And this can be written using measures that if you take a measure which is sum of delta function, its Fourier transform is again the same sum. The measure is invariant under taking Fourier transform. Okay, so, but mathematicians, they are interested in something special, yes? For example, quasicrystals, yes? And of course, if we start speaking about quasicrystals, you should remember Dan Chapman. This is a Nobel Prize, I don't remember, 11, I think, yes? And Paul Steinhardt is here, who actually invented the name quasicrystal. So mathematicians define quasicrystals in 3 equivalent ways. First of all, they look at all the difference between lambda and lambda. Lambda is a set, all the differences. This is the set of reflections. So this is a set of all distances between the points in the set. And the definition that is contained in a finite distortion of these lattices. Yes. The third definition, that this is simply a dland set. Okay. So lambda supposed to be a dland. And then the second definition is that lambda is a Cartan projector or Meillard set. This is obtained in the following way: you take a regular lattice, yes, then you choose a line which has, say, irrational angle. You take a strip close to this line, and you mark all the points which are inside this strip. Then you project it to the line. You get a certain set. This is called Cartan project set. And surprising thing that these 3 definitions are equivalent. This is a Lagrange theorem from '96. With these sets, you can associate Poisson formula. Yes. So you put delta functions at the points on this set. Yes. And you calculate the Fourier transform. The Fourier transform is given by a sum of delta functions. So this is a countable set of points because they belong to the dual lattice. But here you get projections of the points from the dual lattice to this line.
One question. So in particular, if a quasicrystal is not a lattice, then it's contained in a lower dimensional subspace. Like
yes.
it's cut and yes.
Yes, it's a lower dimensional subspace. You can have it any dimension smaller than the original lattice. Yes, and of course, if the angle is rational, then you get something which is periodic. Irrational, this is not periodic, it's quasi-periodic. But the main thing is the following, that if you look at all these projections, they don't form a discrete set. They form a set which is dense. So it means that.
But I think the lattice is in higher dimension, right?
Yes, the lattice is in the higher
Higher dimension, so.
I see. Okay.
Take a lattice in the many dimensions, and then you project on a lower dimensional.
Which are the dimension D that we are studying the
That we
problem.
started with,
Oh,
yes.
okay, then I had misunderstood. Thank you very much.
But it's very good to ask questions. So please continue, yes? So it means that this set is not discrete, so this lambda can be chosen discrete, but this will not be discrete. So is it possible to do better? And Yves Meyer, I think, at least he popularized this. He introduced crystalline measures. So the crystalline measures are defined as follows. These are atomic measures, so it means that the sum of delta functions supported by a discrete set. Lambda is a discrete set. It should be a temporal distribution. You can take Fourier transform, and the Fourier transform should be given again by a sum of delta functions with some amplitudes. You can have some amplitudes here. The most important thing that this set S, which is called the spectrum, is again discrete. And of course, here you again have Poisson summation. The example of these sets that they exist. This is for example, the Scott Dirac comp. So this is a set of points which are equally distributed on equal distance, the delta function. Then this is an example of this crystalline measure. The question is whether there exist other crystalline measures. Yes. Also, there is a generalization of this, the Fourier quasicrystal. It is defined by the following. In addition to all this, you require that the absolute values of the both measures are temporal distributions. Okay. So these are called Fourier quasicrystals in order to distinguish them from quasicrystals I have been speaking 1 minute ago. But actually, Yves Meyer, he calls this quasicrystal. Okay, so first of all, I have to remind you about our paper that we wrote with Peter 4 years ago. So how to construct one-dimensional quasicrystal? The construction goes as follows. First of all, you take a stable polynomial, which is called Lie-Yang polynomial. Stable means that there are no zeros inside the unit disk. So you require that polynomial is stable. It's invariant under involution. So instead of every variable, you put 1 over the same variable. And then you multiply by a monomial in order to make it polynomial. And then you get the polynomial back. Then you assume normalization condition.
Just one question.
Yeah.
Stable Z are real or complex?
Complex. So this is for all zeta with when all the coordinates are less than 1. The absolute value of all variables is less than 1, so they should be complex.
So does the fact that it's invariant under involution then mean that all roots at magnitude 1 are?
So what?
Does the involution condition not then eliminate roots outside of the magnitude?
No, there are no roots inside the disk. And then from here, you can also deduce that there are no roots when all zeta, absolute values of zeta are greater than.
Okay.
Yeah, but it's not a complement.
So yes, but there are roots in between.
Okay.
A lot, actually. For some reason, in complex analysis, this disk and the adjoint disk, they play a very important role, but there is a lot of space in between. Okay, so and then you consider a vector with positive entries, lengths somehow, and then you take exponential of this. So this is a k scalar k multiplied by a. So it means that this will be a n complex variables. You take e to the power ikl1, ikl2, and so on, and then you plug into the polynomial. But then you will get a trigonometric polynomial because it can be written in this form with certain frequencies gamma. So this is a trigonometric polynomial, and you can prove that this polynomial has only real zeros. So this is a real rooted polynomial. How do you prove this? So assume that imaginary part of k is positive. Then all the variables that you put here, they will have a negative imaginary part there. So it means that the absolute value will be less than 1. But p capital was a stable polynomial. There are no zeros there. And the same thing happens if the imaginary part is less than 0. Symmetric, yes? And actually this comes from studies of spectra of Laplacians on metric graphs. Yes. So I can just make an advertisement of the book that was published this year, where these problems are studied. But now I continue about this abstract thing. So you do the following thing. You define the zero set of this polynomial. These are these numbers k, where this is 0, are all real. Yes. How can you visualize this? So you take this is a real representation of the torus. So we all the zeros are real. So it means that actually all zeta that we have to put here, they're on the torus, they have absolute value 1. This is interesting area, yes? So, and then you take a real representation of this torus. So this is a square or a cube, yes? And then you plot the zero set of this big polynomial p. So that the zero set of p is given by certain hypersurfaces. Yes? So how do you get this case? So you take a line with the angles defined with the angles defined by these L1 and L2 coordinates. Yes. So this should be interesting case when this angle is irrational. Yes. So when this line crosses the curve, you get k. Crosses second time, you get the second k. Then the line was continuous. Yeah, you get a lot of infinitely many zeros. Yes. And if the angle is irrational, or if this all these L are rationally independent, yes, then this line fills the cube density. So you are getting the spectrum of this. Okay. So, but you can also have a little bit slightly different point of view. Consider the unit disk. This is where all zeta have absolute value less than 1. The adjoint disk where these are greater than 1. And you define the logarithm of absolute value function. This is we define it coordinate. Yes. Then this log function maps the disk, unit disk, into negative quartile. Yeah. The set in R where all the coordinates are negative. This d star is mapped to R plus the power. Yes. So what happens to the zero set? You see? So the original zero set is defined in Cn, but if I take this logarithm function, I'm getting Rn, yes? So where does this zero set map? So it's mapped to some hypersurface, which avoids these two quartiles, where all coordinates are negative or coordinates are positive. And this can be formulated with the help of var function. Var function, this is the following thing. You take a real vector, yes, let's say with non-zero vectors, and then you look how many times, if you go along this vector, how many times you change the sign. Yes, so then var log is equal to 0. It means that log doesn't change sign. So it means that all numbers here are negative or all positive. So, and then this is another proof that the spectrum is real, that var log of this is equal to 0 for k non-real, yes? Because either these numbers are greater than 1 or less than 1, absolute values. So it means that the intersection is on the torus, but actually the torus by this map is mapped to one point. It means that the torus, this is the set where everything happens, is mapped to one point. One can think that this is a bad map for this problem, yes? But it's not, because with the help of this log, we can prove the real rootedness of this polynomial. Okay, so I have to.
Sorry, what intersection is on the torus?
Intersection what? Intersection between the line e to the power kl, yes,
The secular man.
and the zero manifold of the polynomial. And it's only on the torus.
So the proof given here, it's more or less the same proof you had given.
Yeah, it's the same. I just wanted to establish another language. So it's just repetitions. You see, I was told that to learn something, you have to repeat.
So you're saying that if var is 0, then everyone is 0, and then the previous.
Yes.
Okay.
Okay. So, and then if you consider the measure which is supported by the zeros of this polynomial, then integrating the logarithmic derivative of this trigonometric polynomial, the jump of it on the real axis, you can prove a summation formula, which is analogous to Poisson summation formula. On the left-hand side, you have a sum of delta functions. So if you apply it to a certain function h, it will be the values of function h at these zeros of this polynomial. And on the right, you have a values of the Fourier transform with explicitly calculatable coefficient bj, and this sj. These are simply all the numbers which are scalar products of n and l. L, this is the vector of lengths, which was positive. And n, this is a set of positive integers. So it means that either this is the sum of L with positive coefficients or with negative. So they're positive or negative. And therefore, this is a discrete set. If you take here not positive element with different signs, then you will get a set which is not discrete. Okay, and this was published 4 years ago. Part of this will be published soon, hopefully. And but somehow, since this paper was published, there was few interesting developments in this area. First of all, Yves Meyer, he came with at least 4 different constructions of crystalline measures. Somehow, I think that what happened that he knew a lot of machinery that he tried to prove, to construct these measures. And then he put this example into his machinery.
Excuse me, so just a clarification, the measures we constructed before of this.
No, we were the first to construct measures which are Delaunay, supported by Delaunay sets.
Okay. But the condition about the.
And actually, they have more properties, that they are positive. And actually, the coefficients, you see, in the definition of this crystalline measure, here you allow different coefficients. In our measures, these coefficients are equal to 1. And this is rather unique, because if you have this with coefficient equal to 1, then you can multiply this measure by any trigonometric polynomial. and then you will get a measure with coefficients which are non-equal to 1. But how to get equal to 1? This is
Are they Fourier Quasicrystals as well? or
yes,
not?
they're also Fourier Quasicrystals.
Okay, okay, that was.
Very good question. They are not only crystalline measures; they are also Fourier Quasicrystals. Okay, so first of all, there were several constructions by Meyer, but then Lev and Olevsky they look at the following thing. This polynomial that was important in our construction was real-rooted. And then they decided to start from real-rooted polynomials. And they proved that every Fourier quasicrystal with unit masses, these unit coefficients or positive integer coefficients, come from real-rooted exponential polynomials. And then these Lior and Xintia, together with Cohen, they proved that every real-rooted polynomial comes from our construction. So it means that our construction gives all Fourier quasicrystals in dimension 1 with weights 1 or positive integers. So the construction is very general. So of course the question is how to proceed and continue, and how to get multidimensional quasicrystals. Of course, we should exclude some puzzle examples of these crystals. You take one-dimensional quasicrystals, you take a tensor product, you get a two-dimensional, you multiply by a trigonometric polynomial, you take arbitrarily linear combination of these. These are basal two-dimensional quasicrystals. We want to have those which are not. Okay, and we saw, and actually one can see two possible ways to do this. The first thing is generalizing our construction directly, like, let's say, generalizing somehow these Lie-Yang polynomials and so on. Yes. The other possibility is to follow Olevsky-Ulanovsky approach, which started from real-rooted polynomials directly. Yes. So, and this has been done by Meyer, who, unfortunately, he is working too fast. But he already published at least 3 papers where these measures were constructed using lighthouses. This is a very poetic notion. You should read about this. So then we also did similar thing, but we didn't accomplish this. With Matthew de Courcy-Island, who also has been here. And then there is another construction of Lawton and Zich, who also use these trigonometric polynomials in several variables. So the idea is the following, that you consider real valued trigonometric polynomials, and then let's say 2 polynomials, and then you consider the intersections of the 0 sets. And this gives you, under certain special conditions, this gives you crystalline measures in Fourier quasicrystals. Okay, but now I am going to describe this construction. So, are there any questions? No. Okay, so first of all, the first ingredient of our construction was the Lie-Yang polynomial. But actually, we did not use Lie-Yang polynomial. We were interested in the 0 set of the Lie-Yang polynomial. Yes. Therefore, we are going to generalize not the polynomial, but the 0 set. So we introduced the definition of so-called strict Lie-Yang variety. So strict Lie-Yang variety is a variety which is invariant under involution. Since the Lie-Yang polynomial was invariant under involution, the 0 set is also invariant under involution. Yes? Then we want to construct a quasicrystal in dimension D. Yeah? Therefore, we take a big dimension at Cn or Pn, where in projective space where we consider our variety, and fix also this D. So it means that this variety will have dimension C, will have codimension D. Yes. And then we require that the zero set, not zero set, the variety is lying in the octants where this variation is greater than D. So the variation is big. Do remember that for our construction, the zero set was lying in the octants where this variation was non-zero, was greater or equal than 1. Now it's greater or equal to 0. And then we need also this third condition. But this condition we need for technical reasons, that the intersection of x with the unit torus is contained in the smooth part of x, that there are no singularities on the torus. So this is analog of the Lie-Yang polynomial, the zero set. So then instead of the vector L, we take a matrix. A matrix such that this is n times d matrix, such that all its principal minors are positive. So the vector L was positive, now we have all minors are positive, yes? And then the analog of the zero set is the following thing. We take a vector from Rd, multiply this matrix, we get a vector from Rn, then we take exponential, yes, and then this point should belong to the variety. So it's like intersection point between all these points, they form a variety, yes, a manifold. And then intersection between this manifold and the variety x gives us some set lambda. And we are going to prove that this set lambda, first of all, it is real. It's not obvious that it is real. I cheated you. This W was from CD. Yes. But then we prove that this is actually real. So you take it from CD, multiply by real matrix L, take exponential. So first of all, we prove that this set is real. Then it's dλand set, and it's a Fourier quasicrystal. And to prove this, we are going to go through 5 points. The first point that it is real. The second is it's dλand. Then we prove summation formula. Then we have, after we prove summation formula, we should prove that the spectrum is discrete. Because this is what we are fighting. And then the measure is really a Fourier quasicrystal.
Just one question. So, as a consequence of some of the results you have stated, all of the multidimensional Fourier quasicrystals that you've mentioned in the previous slides, when the dimension is 1, should be obtained by a single Yang or whatever.
Exactly.
Even though it's not completely trivial from the definition.
No, it's not completely trivial.
What is not known in one dimension is if every positive Fourier quasicrystal is of this type. What is known is if it gives mass integers, then it's a theorem. So there may be ones we don't know.
Yes,
But the problem was to classify them. So
But what I was asking is if this new construction, this is not giving something new in dimension 1. This is
no. It's giving something new only in several dimensions. Okay, so first of all, consider positive Grassmannians. These are d-dimensional subspaces in n-dimensional space, which are defined by certain matrix L, and we require that all principal minors are strictly positive. This positive Grassmannian. And then there was an old paper, theorem of Gandmacher and Krein, in their book of 1950, that if you have a positive Grassmannian, then the variation of any vector from V is less than D. So that the variation is less than D. So then let us look at this set of inequalities or inequalities. So you see, if we put this W is from our set lambda. If it is from our set lambda, then this exponential is from x, yes? And the variety x is defined so that the variation of logarithm is greater than equal than d, yes? But on the other hand, the variation of this exponential, of the logarithm of exponential, this is the variation of the imaginary part of v. And calculating the variation, you can get rid of all numbers, multiplication, and then this is a variation of this thing. But this belongs to v, to the positive Grassmannian, and the variation is less than d. So we have d is strictly less than d. So it means that you have a contradiction which proves that the imaginary part of W is 0. So it means that intersection is real. So this is the same as to say that in one-dimensional case, the interesting thing where everything happened was the unit torus. Is the same thing. We are going to work only on the unit torus. But see, oh, sorry, I was a little bit too fast. You see, you have to use that L is Fourier because the minus are strictly positive. So it means that L im is equal to 0 only if im is equal to 0. So we prove that this is real. Okay. So now we want to prove that this is discrete. To prove that this is discrete is it is based on the following fact that we have this manifold that formed by this manifold formed by all numbers of this form, yes, that it intersects the variety transversely. So, and from this you can prove that this set is written actually dland. So, how to do this? So, first of all, in the definition of variety x was the intersection of x with the unit torus is contained in the smooth path. So there is no singularities there. This is important. So now instead of working with x, we are going to introduce its real counterpart. So it's like going to the real parameterization of the torus, yes? So, and if x was a set in n-dimensional space, which avoided these octants, now this set y is periodic. Why? Because you see, if you add integer to this zeta, then you get the same point in x. Yes. So it means that it is periodic in all directions with period 1. Yes. Then x was invariant under this involution. But this corresponds to y invariant after simply complex conjugation. Yes. So then from this you can prove the following thing, that the tangent space to y in complex, so the tangent space considered the complex space is a complex span of the corresponding tangent space in the real space. Yes. So it means that if we have a vector from this tangent space, then, for example, any complex number multiplied by this vector will belong to this tangent space. Yes? So suppose that W belongs to this real tangent space, then IW belongs to the complex. Then we take on this manifold y, we take a smooth path such that at 0 it's equal to x, and the direction is given by this IW. And then for small t, we will have the following thing. So you see, this is something which imitates the derivative, yes? So it means that if t goes to 0, this will go to simply IW. Yes? And, okay. Well, no, this imaginary part, that's why it will go to W. So, mean that it will go to variation of W. Yes? But if I look, if I go this direction, then you see that this belongs to the our variety, so it means that imaginary part is 0. Yes? And then the variation of this is equal to the variation of that, but we have just proven that this belongs to y, this is greater than d. So it means that the variation of w will be greater or equal than d. So here there is this line, but I don't want to explain this. This is just little sophistication. And now what happens then? If we have a vector v from this positive Grassmannian, then the variation of v is less than d. Yes? But if I have w from the tangent space, then the variation is greater than d. They simply belong to different octants. So therefore, this intersection is transversal. Okay. So we continue proving that this is discrete, but somehow you see, we introduced a new set. We had a set lambda. Lambda was a set of all x such that Lx belongs to y. This is because y, this is a all the points which after exponential they map to x, yes? So, but now we introduce a new set, lambda y. So this is set that y plus Lx belongs to y. So lambda 0, this is our old lambda, yes? So, and the first thing is the following, that you take a rational approximation of this L. So you take a matrix with rational entries, which is somehow close to L. Then this set is not empty, contains infinitely many points, because translation by M, this is the common denominator of all these entries in LT. They will give you infinitely many points, so there will be infinitely many sets, yes? And somehow you use that this set is connected to prove that you can approximate this for any L with this rational LT. But there you have to use transversality somehow, that if there was an intersection with rational, then it means that close by there is a intersection with L. So that you can always find a point which is close to the other one. Okay. So how to prove that this is uniformly discrete? So let us remind you that we introduced this set Ly, yes? We introduced two functions. So the first function, this is the smallest norm of x when x belongs to Ly. So it could be 0, could be positive. But this is a function which is continuous with respect to the point. Depends continuously. This is the nearest point to 0 from this set Ly. Yes? And then introduce also the function R1, where you exclude the point 0. So it means that this is the second nearest point of this Ly. Yes? And these two functions are continuous, and moreover, they're periodic in Y. Yes, since they're periodic, so it's enough to look only on the unit cube. Continuous function in the unit cube, they always have uniform estimate from above. Where is it? From above and from no. So they can be estimated from above, but also this function is always stricter than zero. So it means that it can be also estimated from below by a certain r. Yes, and then how to prove that this set is this r capital, this estimate is trivial because you can also say that this r capital is less than n, well, the dimension of space. Okay, but anyway, so how to prove that the set is relatively dense? Suppose we have any point in X, so it means X in RD, so there exists a point Y, which is close to Lx modulus Y. Yes? But then the distance between X and lambda is the same as the distance between 0 and this set lambda with this point Yx. This is exactly R0 of Yx, and this is less than R. So the distance between any point X and set lambda will be less than this capital R. So it means that these points of lambda are situated everywhere in the space. Yes, in a R neighborhood of any point in the space. So this is relatively dense. So now we take two different points from lambda. You have to prove that there is a minimal distance, but the minimal distance is given by this function R1, which is greater than R small. So it means that this is a dland. So what we have proven that the set lambda is real and it's discrete and dland. So summation formula. So now we have to say a few words about these Lie-Yang varieties. Unfortunately, I only can use picture from 2 dimensions, where this corresponds to 1 dimension, but it will help us to understand what is going on. So we are going to speak with indices, subsets of indices. They always ordered, and they will always see elements in this subsequence. Yes. So we take a projection from n-dimensional space to these coordinates with the corresponding indices. So it can be seen as a projection from n-dimensional space to c-dimensional space. Yes. So now important thing is the following. Every point X from this intersection is the smooth point on the variety. And from this you can prove that this projection is unramified, so there are no singularities. So, and from this you can deduce that this is a covering map. So so for example, here you can see that, for example, if we project onto this axis, yes, then it is covered, doubly covered. So this is exactly the corresponding polynomial which is behind has degree 2 in this variable. And then if you project to this, it's covered only once. So this is degree 1 in this variable. Okay, and this can be given by such integrals. This is called multi-degree. So they're positive integers. So how do we prove the summation form? So suppose that this is this variety. So then you introduce a measure. You introduce the measure in the formula. So this is supposed to be this variety. You have a certain direction. So and you make this, you shift this curve in this direction. And then you, for any set A.
Is this I remember how much we struggled to show the absolute convergence.
Yes.
On the other side, you have an easier
Yes.
treatment of that.
Sorry.
In the definition of a Fourier quasicrystal,
Yes.
one can and we do demand that the sum of the absolute values that be tempered, absolutely tempered.
Yes, yes, but
And
this,
we struggled a bit with that.
this will come from this formula.
So this treatment is a simpler treatment than we had, is that it?
No, it's equivalent.
Oh, okay.
Because I don't know which one is simpler. Because do remember, the main thing was the following, that if you have analytic function and you take its logarithm,
Okay.
then it's integrable over any, how's it called? The real manifold.
Yes.
So, and
That's
the same thing. Okay, so you see what, if you have any set A, you consider this volume. Oh, sorry, so it should be in this direction. Yes. Consider this volume, and then you take the limit when epsilon tends to 0. You will get a measure on this curve. So this is the measure that you want to consider. Yes. But
You fatten it, it's called a DeLong, some standard differential, DeLong. Anyway, I call it a Hardy Littlewood measure.
okay, thank you. We'll include this maybe. No. Okay, but also you can consider the basic measures. These are measures which you get by projecting this variety onto different C-dimensional spaces. Yes. And then if you take these basic measures, then its Fourier coefficients are given by this thing or by this formula, this equivalent. Here there is a sign. And one should remember that if variation of k is greater than d, yes, that here in this product, this is a product of all zetas, yes, with powers k, there will be at least one which will cancel with zeta in the denominator. And for this reason, the corresponding coefficient will be 0. So it means that the Fourier coefficients of all these basic measures are in the regions where variation is small. So it was like in our construction, there was Fourier coefficients were non-zero when variation was 0. Now it's simply small, less than d. So, and then one can prove the following formula, that this measure that I introduced here, this will be equal to the linear combination of these basic measures, and these minors, which were positive, they are exactly the coefficients here. So it means that this is a positive linear combination of these basic measures. For example, it will be important in the future that the Fourier coefficient at 0 is equal to the sum of Fourier coefficient at 0 and Fourier coefficient at 0 of this measure. This is exactly this multi-degree. That's positive.
That is the clarity. I mean, the fact that you're using the intersection with your nice variety on the smooth part, this is because you want double cover. Right?
Yes.
But would that converse hold? I mean, if you get double cover, then you're coming from a smooth part. I mean, are you just using the smooth part to have double cover?
Yes.
That's my point.
Yes.
So you could, in principle, start from a.
No, but also for discreteness, I used it before. Because there is no transversality. At least I don't know if it is singular. You can.
So you, okay.
But this may generalize this.
Yeah, that's what.
I think that's what he's asking.
Exactly. So you, in principle.
Okay. So, and then you get a summation formula. How do you get this? You make an approximation of this measure by taking function g, which is equal to some constant here, and decays fast outside. Yes. And then again, you can. This is a periodic function. You have a Fourier series, and Fourier series can be rewritten by moving this L to the left because you want to have it at point Lx. So, but now it looks like the usual Fourier series. Yes. And then if you integrate any reasonable function f with this g, first of all, if you use this Fourier series, of course, you have to work and say that you can exchange integration and summation, but after that you get this thing because integration gives you exactly the Fourier coefficient of f, yes? And then when epsilon tends to 0, therefore this Fourier coefficient goes to the Fourier coefficient of the measure because this function approximates the measure, yes? But if you look at the left-hand side, so here when epsilon tends to 0, it will go to the set sum of the f of x. So we are getting summation form. Okay, so I think I will skip discreteness of the spectrum because this is not, this is rather standard thing here. So the only thing which is important here that you make a resummation in this form, because the original formula that you proved, here was the summation of OK, but here it was f hat of L transform K. But now we have to sum up all the all the K's corresponding to the same psi. But this set is finite due to this, because we only have to sum up where variation is less than d because coefficients are equal to 0 outside this. Okay. And actually it's also a Fourier quasicrystal because it comes from the fact that all the Fourier coefficients are majorized by Fourier coefficient corresponding to 0. But somehow I want to skip this in order to be able to come to the end and show the pictures. So first of all, of course, this set becomes, one can prove that this is Bohr almost periodic. And then one can also say something about its arithmetic properties. So this is direct modification of our proof that the spectra of the zero of one-dimensional measures don't contain one-dimensional, don't contain arithmetic progressions. But now the thing is the following, that they will not contain vector spaces with vector space. But okay, I have also to skip this. And with non-triviality, this is much harder. And actually, we just managed to prove that these measures are somehow non-trivial. But we don't have a complete proof of non-triviality because
Non-trivial means not what you were calling basal.
Basal, yes, non-basal. So
You made this very elaborate construction, and it may well be a simple construction for you.
You mean a product measure?
Yeah, right.
Okay.
So
And so,
linear combinations of
Yeah.
product measures also multiplied by arbitrary exponential polynomials. We only have it assuming Shapiro's conjecture or Shanwei's conjecture.
What does this conjecture say?
Shapiro's conjecture is the following, that if you have two trigonometric polynomials with infinitely many coefficients, then it means that there is a third polynomial which divides both. So you have two,
Okay.
two trigonometric polynomials, and they have infinitely many
trigonometric polynomials with arbitrary frequency.
Yes, with arbitrary frequency, yes. And they have infinitely many common zeros.
Oh, okay.
Yes. Maybe this.
And there's a good reason for it.
So, and then there is a third polynomial which divides both. And this has been proven if these zeros belong to a certain arithmetic sequence. Then it is a zero, but not general. But it follows from Shanwei's conjecture. Okay, so let me give you one example. So we consider the variety which is determined by two polynomials. Yes? So this is this blue curve, because in 3 dimensions, there are 3 dimensions to equations. This is a curve. We take this matrix L, which is this one, minus are equal to 1, square root of 3, square root of 2, they're positive. And somehow the range after this matrix L, this is this orange plane. And each time when curve crosses the plane, you get a measure, a point from this set lambda. So you see, since you have two polynomials, so it means that on the two-dimensional real space, you have two trigonometric polynomials depending on two variables. And they have zero sets. One is blue, the other is brown. When they cross, you get points from this quasicrystal. Yes? And you can see that this is somehow, this is almost periodic. I cannot say anything more. Yes? But if you look at the Fourier side, it looks like this. That in the middle, there are a few points, but outside, they are becoming dense and dense because there is a theorem telling that if the support of the Fourier is dland, so uniformly discrete, then this is a trivial measure. So this is a set of unit positivity. I'm sorry. Then you assume positivity, then this is a trivial measure. This is the simplest combination of Poisson summation.
That's a converse to Poisson summation. So if you have a summation formula where it's positive on the one side, the other side is, well, separated, then Levski show that it has to be Poisson sum or combinations, and that
So
is kind of remarkable. It's classified as Poisson sum.
okay, so one can compare this with existing approaches. For example, with Laldl, they always had only D polynomials, but there are varieties which are of codimension D, which are determined by more than D polynomials. So it means that they are not covered by our construction, but it's not clear whether their construction is always more general than ours. But if the set is dland, then our construction is more general than theirs. But with this Meyer and our construction with Matthew, it's not clear which one is more general. So probably one should look at some kind of combination of these two constructions, because we are getting quasicrystals with non-integer weights directly. Okay, so today you already learned that Princeton got a Nobel Prize. Yes,
You did this last week, right?
yes, yes.
You're coming from Stockholm.
Yeah, of course I do.
Oh, you're not allowed to prepare the
This should
slides.
be cut it. This should be cut it from the recording. Okay, but you see, I try to
By
explain.
the way, Hopfield's got an office right there. We should go see if if he knows that he got the prize.
Seen him in a
I haven't seen him in I've only seen him at dinners.
Okay,
I think he's 94, they say.
anything. So anyway, you can see that behind this one-dimensional quasicrystals, there was some metric graphs and Laplacian symmetric graphs. So I don't know which Laplacians are behind this multidimensional, if there are some, yes? And also somehow playing with one-dimensional quasicrystals for metric graphs, I found out that they have a very solid rigidity. So you cannot change one of the zeros. You have to change infinitely many zeros. Can it be somehow interpreted as a memory storage connected to Nobel Prize? We will see. Okay, anyway, so I have one bonus picture. So this is an example of a quasicrystal in 2 dimensions, but which is determined by 3 trigonometric polynomials. So it means that the support of this quasicrystal is the points where all 3 curves are crossing. For example, this point, here there are 2 claws, again 2 claws. So this picture was produced by Cynthia. So we tried to convince her to send it to some exhibition because this is this reminds modern art, but somehow she has to work a little bit with colors. I think this is the only thing she's missing. Okay, thank you very much for your time.
Are there further questions?
So about the third assumption on your the young variety that this single there are no singularities of the variety on the torus.
Yes.
So thinking about the secular manifold, whatever the one dimensional,
Mhm.
I would be hard pressed to come up with an example of a quantum graph that does not have singularities. Is it? But it's a feature for. Yeah, but what is this?
So this is a Lasso graph.
Well, Lasso graph has sides. Like there is another bit to it.
Yeah, but we threw it away because it's trivial.
Okay, that's.
So
yes. Okay, you can factor by the symmetry and.
The origin wants to be a singularity unless you're a tree, anyway.
But in general, if you have many lengths, you have many parameters, and many parameters for Neumann. And
so no, you do the following thing to see. So for graphs,
yeah,
these varieties will have singularities.
Okay.
But then you can choose the lengths, not rationally independent.
Oh.
But rationally dependent, so that they because if they're rationally dependent, but
then we can avoid,
but not completely, they will fill certain planes, and these planes should avoid the singular points.
Oh, but then you need to know that the dimension of this singularities is high enough so that you can.
Yes, this is called
Collider
conjecture number 2, which we have not proven.
You have not proven. So do you have then a family of examples on? I mean, you just told me an algorithm that depends on conjecture, which has not been proven. So.
No, in one dimension, this is the summation formula. Everything works in one dimension. It is in higher dimension.
But there is no discreteness.
No. This has nothing to do with discreteness. This has to do with uniform discreteness. Because I will go to that. You see, if you have a singularity, so let's say picture which process like this.
Okay.
So then if you process, then there will be points which are very close.
Yes.
But all the time the set will be discrete. Maybe sometimes when you cross through this, you will have a double eigenvalue. But the distance between eigenvalues will always be finite. So it
will always be finite, but there is no limit target. You want the dland, right?
Yes, it will not be dland.
So what is the definition of Fourier? I thought it's dland on both sides.
No.
There's no sense.
No.
If it's dland on both sides.
Then it's regular. That's okay.
No, the situation is the following. It's discrete, simply discrete. But it was believed that it is hard to make sets which are dland, discrete and dland. The dland somehow it's harder to.
Okay. So Fourier quasicrystal is just discrete on both sides.
Yes.
Okay. Thank you. Yes.
But we are also getting those which are dland, because they only
on one side.
Yes, because if it is on both sides.
Then yes, then
there is a
Olevsky theorem.
Levolevsky, but there you need also in several dimensions you need positivity. In one dimension, this is you don't need positivity, but in 2 dimensions and more you need positivity. Then it is a trivial. There is also a counterexample showing that this positivity is really needed.
Questions? Okay, then let's take this.